Okay, let's look at this problem that involves distributed loads as well as resultant force as well as resultant moment principle. If the soil exerts a trapezoidal distribution of load on the bottom of the footing, determine the intensities of W1 and W2 of this distribution needed to support the column loading. All right, so this distribution load, for whatever reason, it's a trapezoidal shape, is as a result of those columns pushing on the footing and the footing pushing on the soil. So soil pushes back with the same amount. So whatever this distributed load is, if it's equivalent to a resultant force, then I know that 60 plus 80 plus 50, which would be 110, so 190, pushing down, total force. I'm just showing total force. The location is not really relevant. Should be the same as FR. So my FR is going to be 190 kilonewtons. So if I can find the equivalent force of these distributed load, then I know the summation of it is 190. But I have two unknowns, and this is just one equation. Once I find the equivalent force, we can use maybe moment equation. Maybe we can use summation of Fx equation to add another equation, so we are able to solve the two unknowns. Summation of forces in X does not help us with anything because there's no forces in X, so this equation is already satisfied and it does not result in an additional equation for us. So we have to go use moment. But let's take it one step at a time. Let's find this equivalent force of this distributed area force first. FR, we know that is equivalent to area under loading, and location of it, wherever we put it, is also going to be centroid of this area, center of this area, or centroid. It's a trapezoid. Might be difficult to find centroid of it. Area we can find, not a problem, but not the centroid. So what I'm going to do is I'm going to divide it into shapes that I can identify easier. So I'm going to have area 1 here, and I will have area 2 here. Sorry. So these are more familiar areas, so I can work with. So FR1 this rectangle has W2 as the width and 6 plus 2, 8 meters as length. So resultant force 1 is this area, so it's 8 meters W2, so it's 8 W2. I have meters there as well. Centroid of this area, centroid is located at the midpoint, so it's half of 8 meters, and that's 4 meters. So if I want to replace area 1, I get FR1 equals 8 W2 located as 4 meters. I'll do the same for second area. This side is 0. This side is W1 minus W2. So same kind of area. I have to calculate area of a triangle, half of its base, multiplied by height, which in this case is the 8 meters. So it's W1 minus W2, 4 meters. Centroid of triangle is located at 1/3 to the base, 2/3 on that side. So 1/3 of 8 meters. I'm just going to write it as 8/3 meters. So let's redraw the shape here quick. I'm drawing the beam, or sorry, the footing, and try to put forces on there. So we have a 50 kilonewton, 80, and a 60. And then I have an FR1 located at 4 meters. So 3.5, got to be a little bit this side, which was 8W2. And the next one, I had FR2, which is located right here, but force is a sliding vector. That means I can slide it on its line of action and kind of bring it down. That's why I brought these forces down and put it directly on the footing as well. Force is a sliding vector. You can slide it up and down on its line of action with no effect on anything else. FR2, and that one was W1 minus W2, 4 meters. All right, as I said before, the goal was to find these W1 and W2. One equation that I had that I can use, since this is an equilibrium, since this distributed load is a result of those forces pushing down, so 60, 80, these are all negative, sorry, because they're going against my sign, and 50 plus, plus 8W2 plus W2 4 should equal to 0. Two unknowns, I can't do anything about it. I'm just going to leave it like this for now. Let's look at moment equation. So you can take moment about any point, A, B, C, D, any point you want. But I'm going to take it about a point that makes my life a little bit easier. I'm going to take the moment about this point right here. The reason I do that is because then this force, this FR2, passes through point B, and when I do summation of my moments about point B, I don't have to calculate that. Why? Why is that helpful? Then I'm just left with one unknown, and I can just write one equation and find that one unknown. You can again take moment about any point you want. You can take it about B, you can take it about C if C is here, you can take it about D, whichever you want. It does not matter, and it should result in the same thing. So let's take moment, summation of moment about point B. That should be 0. Anything that goes this direction, I'm going to take it as positive. I have, so we'll count all the forces, and we'll look at each force. Okay, I'm going to write down the distances here quick, so it's easier to keep track of it. Whatever I calculated, this one was 8/3, and these are all meters. This one is 4. This one right here is 1 meter. The distance between the two is 2.5. I know these are up there as well, but like to write it so I can keep track of it. All right, so let's start with the moment. So we'll go one by one. Let's start with 60 kilonewton, and the distance between this force and point B, perpendicular distance, line of action of this force and point B, is 8/3 minus 1. That's meters. And it's trying to rotate this way, so that's positive. Next, I go to the 80. I go a little bit faster now. 80 kilonewton, the distance between this one and point B is 3.5 minus 8/3, and that's meters. And this one is trying to rotate this way against my sign, so that will be negative. Next, I move on to the 50 kilonewtons. The distance between this one and point B is 7 minus 8/3 meters. And this is rotating this way, which is against my sign, so that's also negative. And then I have FR2. FR2, the distance between that one and point B is 0. You don't have to write it. I just wanted to show you that even if you write it, the distance is 0. It goes through point B. Plus, minus doesn't really matter. There's no moment. And then FR1, well, let me just write 8W2 right away. And that one should be 4 minus 8/3. That's meters, and this one also has meters and meters in it. It's trying to rotate this way, which is with my sign, so that's positive, and that will be 0. Sorry, it's a little bit messy, but if you solve for W2, the only unknown is W2 right here. If you solve for W2, you will get W2 equals 1.87 kilonewtons per meters. So since this is one of the answers that it's asking for, I'm going to round it up to 3 significant figures. That's the standard that we do for statics class, and that's my W2. So I'm going to put this one back, not the rounded one, but this number back in here and solve for W1 in my F1. If you do this one, if you plug the 1.87 kilonewton per meter on there, you will get W1 equals to 312 kilonewtons per meter. If I want to round it to 3 sig figures, we'll go 30.3 kilonewtons per meter for W1. Thank you very much.